Hey, it's Mr. K doing a video for AP Physics 2. We're going to talk about Young's double slit. This is one of the main experiments to define light as a wave and not just a particle. There was a big argument back then when they said, hey, light has to be a particle. No, it has to be a wave. No, it has to be a particle. And it has to be a wave. Well, several experiments showed that it's both. And so scientists finally decided, okay, yeah, light acts like a particle in some cases, but it also acts like a wave in other cases. So Young's double slit is one way that it definitely looks and it behaves as if it was a wave. And so what this is let's just draw it out here and do a little diagram. We're going to have a gap. We're going to have another one. So we have this wall, and there's a hole here, and there's a hole over there. And so we're going to treat light like, let's say, ocean waves coming in. Pretend this is like a harbor. And so waves are coming in, and when the waves hit either gap, what they do is they will ripple out from that gap. And so these waves that ripple out from this one, or ripple out from that one, as they get to travel, so this is the oldest wave right here, they will begin to interact with the waves from the bottom gap. And if you notice, right here in the middle, they are, well, if you call these crests, they would be crest and crest, which would mean that they would be constructively interfering. And in terms of physical waves, like waves in the ocean, they would get taller. In terms of light waves, they would get brighter. Now, if you have constructive interference, that means that in between where you have a crest and a open space, which would be a trough, then you would have the opposite of constructive interference, which would be destructive interference. So the superposition of those two waves would be canceled out, or essentially nothing. And so if you allow these waves to go, and let's say they were to hit a wall somewhere over here, then right in the middle, you would have a bright spot. And as you started to go out, you'd have a dark spot or a dark band on either side. But then as you started to go farther out, you'd get a bright band. I'll try to video edit this to show a picture of the double slit interference as well as single slit interference, if I get a good picture of it. But the reason why that is because if you have this wall, this is your projection, and we'll do this experiment in class, but you have a distance to travel to get here. And if we talk about a distance to travel to get here from the top hole compared to the bottom, so let me use a different color. What you should notice is that the distance from the top and the distance from the bottom hole to the middle part here should be exactly the same. And if waves act like waves, if they start off and they're allowed to fluctuate as waves do, then when they travel the exact same distance, then you should be in the same phase or the same part of the wave. And so here you would have addition, and we would see that addition as a bright spot. But if you allowed the waves to travel just a little bit farther, not here, but let's say we traveled a little bit farther there, then what would happen is that these two waves would be in total opposite parts of the wave. And a crest and a opposite trough would cancel out, and we would get nothingness. And in the case of visible light, we would get a dark spot. And so what you see is this pattern of bright, dark, bright, dark, bright, dark that would appear on the wall. And the spacing is really, really tiny, depending on how far away your wall is. And so you get a really pretty diffraction pattern from this. And this is called diffraction, where waves ripple out from holes. And so we have reflection, where the waves would bounce off. We have refraction, where they'd go through, slow down, bend a little bit. And then we have diffraction, where they would ripple out and be like new sources as they went through these gaps here. And so Young's double slit is the experiment where they showed, hey, light definitely acts like a wave in this case, because what you would expect if you had two holes here would be like a bright spot and a bright spot with a dark spot in between. But you get not that. You get a bright spot in between, and then dark spot, bright spot, dark spot, bright spot. And so the reason why that is, and we're going to draw it again, is that, let's make this a bit bigger. And the reason for that is that this distance is really, really, really big. And if you call this distance really, really, really big, then as these waves travel there, then yeah, you're going to get this constructive and destructive interference. But the benefit of that, and the way we're going to do the diagram, is imagine you're going to point at something really far away. And if you point at something really, really far away, and then I said, hey, okay, point to the thing next to that. You're like, hey, I'm still pointing at that thing. Let's say you're at the football field and you're pointing at the goalpost at the other end of the football field. And I said, all right, point at the guy that's standing right next to the goalpost, and your finger would not even move, right? And so the way that we're going to do the diagram is we're going to say, all right, these two waves are essentially going to be parallel because we're essentially pointing at the exact same place, even though we know that one wave is going to travel just a bit farther. Let's say we're pointing at somewhere down here. All right, and to get here, again, we're going to have to travel from that top spot and travel from that bottom spot. And if you note, on this diagram, you can definitely see that this top black one, compared to the bottom black one, is a little bit longer. Now, the angle, you can say, oh, that's different. Well, that's because this thing is really short. But remember, this experiment's done where you have a really, really large distance L here, and this, let's call this little d there. This distance L is like thousands of, hundreds of thousands of times whatever this distance, this separation d is. Okay? And so if that's the case, then we can go down to this diagram and say, all right, these two lines are essentially parallel. And when they hit that wall, the black one should have gone a little bit farther than the purple one. And the black one goes a little bit farther because of this distance right here. If you cut this little piece off, then they are the same length, or should be. Okay? So the question is, what the heck is this? So this little piece, we've got this separation distance d, that's going to be this side of the triangle. Remember that this needs to be on the order of the wave size that you're using. So if you're using water waves, that could be like a rock, all right, or like a post in the middle of the ocean. For light waves, this thing needs to be like the size of a hair, or smaller. Light waves are really, really small, like 700, 600, 500 nanometers. And this distance is going to be like 20 meters or something like that across. So we've got this angle here, theta. We've got this distance here. We've got this thing here. And the key that we're looking for is for this distance to get a bright spot, to be one wavelength. Because if we are moving and we go and we go a little bit farther, we want to be right here again. Oops. We want to be right here again in order for us to get constructive interference for this first bright spot. So these two waves of light, this ray up here, there's a bunch of rays, we're just picking these two. This ray has to travel just one wavelength farther than this bottom one in order for it to be constructive interference. If it travels a half wavelength or 1.5 wavelengths, then it's going to be destructive interference. You're going to get a dark spot. All right. Right in the middle, they would have traveled the exact same distance, and so you get the bright spot. But a little bit down, top one travels a little bit farther. If that little bit farther is one wavelength, then you're golden, and you get constructive interference. So there's a relationship here on the micro scale that we can compare to the macro scale. And what that is these two sides, I can say, okay, this is the, what is this? Is this the adjacent side, or is this the hypotenuse side? Well, if I made that 90 degrees, then this would have to be the hypotenuse side. But the benefit of the diagram that we're doing is that the adjacent side and the hypotenuse should approximately be the same length. And what happens there is we can say, all right, the sine of theta should equal the tangent of theta, which equals theta in the end if it's really, really, really small. Okay, this is called small angle approximation. So sine is what? Opposite over hypotenuse. Tangent is going to be opposite over adjacent. And what you should see here is that as the adjacent side and the hypotenuse side are pretty much the same length, yeah, sine and tangent become the same value. So what we're looking at is the sine of theta, whatever this theta value is going to be opposite which what we want right now is going to be a wavelength, one wavelength, divided by this width here, this separation of these two holes. Okay, and then what we're going to do is we're going to liken that to where this bright spot is. So if we talk about this bright spot, this first bright spot right here, we're going to go down, or we can even go up. This right here is going to be, I'm going to call it some x. And we have this distance L. We've got this x, which means that we have another triangle, right? And so this distance L should be very, very, very large compared to however far this distance x is. So we can use sine or tangent, really doesn't matter. I'm going to use tangent because I just feel like it. So up here I can say tangent of theta should be equal to x divided by L. And using our small angle approximation, we should be able to set tangent and sine equal to each other, which means that the wavelength divided by the slit separation d is equal to x divided by L. Okay? And for our first order bright spot, that's where our path difference is just a wavelength. That's going to be an x value there. If we want the second order, what I would do is I would actually put an n right there, and I would put a 2 in place of that n, or a 3, or a 4, or a 5 for all these bright spots that would appear. All the dark spots would appear in between those bright spots. So if you really wanted to find it, you can find that bright spot, just divide that distance x by 2. And so what you would get is, well, let's see. How should I solve this? Let's go ahead and let's just move the L over. So n wavelength L divided by d is equal to my separation x. So for the first order bright spot, it would be just n is 1, the wavelength times L divided by d. So if you were to run just a sample problem, we can say, all right, the wavelength is about 700 nanometers, so 700 times 10 to the negative 9th meters. The length of the room, what did I say earlier, like 20? Let's make it like, yeah, let's make it 20. 20 meters from the back of the room to the front of the room. That's probably a bit far. And then D is, let's leave that as the unknown. And then X, let's say somebody went to the very front of the room and we projected this diffraction pattern onto the front board, and they measured X to be about 1.5, about maybe 2 centimeters. So 0.02 meters. Okay, the separation of these bright and dark spots is going to be really, really close. And so all we would do is we would run back here and we'd say, hey, this was the first order bright spot. I would say that's 1. This is going to be 700 times 10 to the negative 9. 20 is going to be there for L. And D is going to be, I don't know. But tell you what, let's go ahead and switch the positions of these because I want to know what D is. So X is going to be down here. X was 0.02. And that would be equal to D. So running it through, we could say 700 times 10 to the negative 9 times 20 divided by 0.02. And that gives us a 0.0007 length for D, which is 7 times 10 to the negative 4. 7 times 10 to the negative 4. Almost a millimeter. Almost. So that's going to be super small, but that's what we would get if we were to do this experiment in the classroom. It's something really, really small. So again, Young's double slit, you have light coming from two sources that are really, really close together. It needs to be on the same order as the wavelength of that light. And, well, sort of the same order. And you get this separation based on this really, really far distance. And this shows that light acts like a wave. It does act like a particle in other cases, but in this case, it's going to act like a wave. Now, with a single slit experiment, the bright spot in the middle is going to be super bright, and then the dark and bright bands on the side are going to be very, very, or the bright bands on the side are going to be very, very dim. Whereas with the true double slit, the brightness of these spots are pretty much the same until you start to get to like the third or fourth order. The first and second order are definitely about the same brightness with Young's double slit. So we'll end that here. Hopefully I can find a picture that I can embed in the video. We will see. But stay tuned.